In the previous module, we discussed the different types of tests of significance, using which you can compare two sets of data. Comparison between certain expected values and certain experimental observations, or comparison between two sets of experimental results obtained from two populations or two samples. And for the purpose, we used chi-square test or t-test. And the major limitation of this type of test is that you can compare only two sets of data, population 1, population 2, sample 1, sample 2, or observed group of data, expected data, like that. But in practice, usually in experiments, you may be in need of analyzing several treatments together, several samples together. The differences in the behavior of variables in several samples or under different treatment conditions. So there will be more sets of data, more than two sets of data, 3, 4, 5, like that. There you will have several sets of data. And when you want to analyze a particular variable, in the case of all these sets simultaneously, or if you want to analyze a group of variables together, or if you want to classify and cross-classify phenomena, and if you want to find out whether one way of classification gives significant result and the other way of classification gives significant result. Under such circumstances, it is not possible to use this type of tests like t-test or chi-square test. Under such circumstances, we go for a higher level of analysis, and the analysis pattern is usually called analysis of variance or Anova, analysis of variance. And in analysis of variance, we are comparing a variable as it is expressed in different populations, in different samples or in different treatments. So you will be having, instead of a single series of X, you will be having several such series. For example, you can say there is x1, x2, x3 like that, and each series will be having a mean and a standard deviation like that. So under such circumstances, you have to use analysis of variance. And this is also a type of test, and this test statistic that is calculated is F. The F value is calculated. The pattern of analysis is called analysis of variance, and it is called Anova also. And if you are considering only one variable at a time, you use a one-way analysis of variance or a one-way classification. And if you want to consider more number of characters or parameters or properties together, you use two-way Anova, for example. In either case, in both these cases, the test criterion is, the test statistic is F. And simply speaking, F is the ratio between the variation shown by different samples and the variation shown by a single sample or the variation within the sample. So it is a comparison. F is a comparison between the variation that is occurring between the samples or between the treatments and the variation that is occurring within the treatments. And there is a general assumption that the variation between samples or the variation between treatments may be due to sample differences or treatment differences, and the variation within treatments or within samples may be due to chance, due to experimental error. So that is the idea behind calculation of the F value, and it is calculated using a formula F is equal to variance between samples divided by variance within samples, or variance between treatments divided by variance within treatments. And when you get a higher F value, it means that the denominator of the equation is higher, means between sample variation is high, and the denominator is smaller. F is higher, means the samples have difference in properties. The variable behaves differently in these samples. The variable behaves differently under these different treatments. So that is about analysis of variance as an introduction. And as mentioned, F is calculated using a formula is equal to variance between samples or variance between treatments divided by variance within samples or variance within treatments. And here also, F as you know, it is a calculated value, it is a test statistic, and here also you are using an F table to see whether the variation or the F value is significant or not. For that purpose, you will be taking a decision on the critical region, and the critical value will be taken based on the critical region or the percentage, the level of probability at which you are considering the significance, the level of significance of the test statistic. So it is the ratio between, or you get F value when you divide between treatment variance within treatment variance. So it's a little lengthy procedure, there are different steps involved. And the first step is to calculate between sample variance or between treatment variance. And for that purpose, first you are finding out the means of each sample, or you are finding out the means of each treatment. You will be given data in the form of a table, and you have to draw mean columns, and you have to calculate mean for each sample or mean for each treatment one by one. For example, if there are 5 treatments or if there are 5 samples, you will get mean for the first sample, mean for the second sample, mean for the third sample, mean for the fifth sample, like that. And when you calculate these values, the means, you have to find out the combined mean of these samples or treatments. You have to calculate the mean of the means so that you get the combined mean. And the next step is to calculate the deviation, the variation of the combined mean from the means of each sample. The combined mean, since it is the mean of the mean values of each sample or mean values of each treatment, you can find out the difference. If you are considering x double bar as the grand mean of the sample, you can grand mean of the samples or grand mean of the treatments, you can find out the grand mean, finding out the mean of the sample means. And in each case, you will get, for example, you will get an x bar minus x double bar, for example. The mean minus the combined mean. You get different values for each sample or each treatment. You get one value, and then you have to square them. If there are 5 treatments, you will be having 5 values, or if there are 5 samples, you will be having 5 values, and you will be squaring the deviations to get the d square. And you will be multiplying the number of replications in each sample treatment with it, and you will be finding out the sum of the variations. The value thus obtained is the sum of squares of the variation between samples, and you will be getting this sum of the variations, and the value obtained is the sum of squares of the variations between samples, and you then divide the sum of squares between samples or the sum of squares between treatments with the treatment degree of freedom. If there are k number of treatments, treatment degree of freedom is k minus 1, and so from the sum of squares, if you are finding out the mean, you get the mean square values, and the mean square of deviations stands for variance. So now you have calculated the variance between treatments or variance between samples. And then comes the next step. The next step is calculation of within sample or within treatment variation. Within sample variation or within treatment variance. For the purpose, you are finding out the deviations of the replications, each and every replication from the particular sample mean or the treatment mean. Each value of your observation in the case of each replication, from each value you will be taking the difference of the corresponding x bar, and you get the deviations, and then you are squaring the deviations and finding out the sum, and when you are finding out the total of all the treatments or all the samples, you get the sum of square values, and it is called, or this is the sum of square within sample, sum of square within treatment. Then when you are dividing it with the degree of freedom, and in the case of within treatment, degree of freedom, it is n minus k. Between treatment, degree of freedom is k minus 1, and within treatment, degree of freedom is n minus k, and the value obtained is the mean square. In the case of mean square or the variance within sample, or the mean square within treatments. And the next step is the construction of the Anova table. And the Anova table is a table that is usually constructed for analysis of variance, and there are different columns. In the first column, the sources of variation are given. In the second column, the sum of square values are given, and in the third column, the degrees of freedom are given. And in the fourth column, you get the mean square. So there are two sources of variations between samples or treatments and within samples or treatments. And of course, you can give a third row, a total, and sum of square corresponding to between sample variation or between treatment variation is called SSB. So you can say sum of square between variation within samples or within treatments is SSW. Sum of square within, and total means you are just summing out both of them. And degrees of freedom, in the first case, between samples or between treatments, it is k minus 1 because there are k treatments, and within treatment, degrees of freedom is n minus k. N is the total number of units of observation together, and k is the number of treatments. So mean square is equal to, and the total degree of freedom will be n minus 1, and n minus 1 is obtained by adding k minus 1 with n minus k. So that is total degree of freedom. And the mean square is calculated by dividing the concerned sum of square value with the degree of freedom, and there are two such values then: the mean square between samples or treatments and the mean square within samples or treatments. And the mean squares are, as you know, mean square variation is variance. So they give you the variance between treatment variance and within treatment variance. And then you are calculating the F value. F value is calculated using the formula F is equal to variance between samples or treatments divided by variance within samples or treatments. Mean square value is calculated in each row above they correspond to the variance. Mean square is the variance, or mean square variation is the variance. So mean square variation in the between treatments divided by mean square variation within treatments will be giving you the F value, and then you will be using an F table to test the significance of the F value, and for that you are using an F table. So now you can move to an example. Calculation of F value and finding out whether it is statistically significant or not. So an example is given. Calculation of F value in the case of treatments of 4 doses of fertilizer made in a plant population to test whether the dose differences have significant impact on plant growth in the first year, several seedlings have been planted, and you are dividing the plot into different blocks, and in each block you are giving a particular treatment. For example, you can say there are 5 treatments, treatment 1, 2, 3, 4 and 5. Let it be different doses of a fertilizer. You see, a higher dose of a fertilizer means higher cost involved. So you have to decide what is the optimum dose needed so that there is good yield without very high expenditure. So for the purpose, you are testing whether there is any difference between the treatments. And for example, if treatment 1 is a blank treatment, a blank control, for example, you are not applying any fertilizer, and if you are applying, for example, annually you are applying half kg, 1 kg, 1.5 kg, 2 kg, like that. If it is an organic fertilizer, for example, and now the fertilizer cost is high, and with the minimum dose of fertilizer, minimum quantity of fertilizer, you want to get higher yield, so you have to standardize it. So you have a treatment plot, and you have divided into 5 blocks, and in each block you are giving a fertilizer treatment. In the first block, for example, it is treatment 1. Maybe it is control, and there is no significant variation in the case of any other treatment. There is no need of applying that fertilizer itself. So number 2, 3, 4, 5 treatments. Maybe 2, 3, 4 and 5 are different doses, and number 1 is a blank treatment, for example. And you have to carry out the experiment or repeat the experiment sufficient number of times. And there are certain rules behind it. And in the present example, in the present experiment we have done the experiment with 3 replications. We have replicated the treatment 3 times. And so there are 5 treatments and 3 replications that are given in the table. Treatments are given, plant height at 1 year of age are given, also data of replication 1, replication 2, replication 3, etc. also are given to you. And you have the mean also, the mean values of each treatment also are given here, and usually you will have to calculate it in each row. For each treatment you have to find out the mean. So that is the first step of the analysis, calculation. You have to find out the treatment means, or the treatment stands for sample itself, sample means. So there will be, for each treatment there will be different mean, and there will be a combined mean for the treatments together. So that you are obtaining by finding out the mean of the mean values of each, the mean of the mean values of each treatment. So you have calculated the mean of each treatment and the combined mean. And the next step is calculation of between treatment variance, or calculation of between treatment sum of square first. Between treatment mean square is the variance between treatment. So before finding out the mean score, you have to calculate the total of the squared deviations, and evidently you are squaring deviations because you want all values to be positive. So x minus X bar in each case, the mean, the corresponding sample mean, when minused with the grand mean, the combined mean, will be giving you the corresponding D. So for the first treatment there will be a D value, for the second treatment there will be a D value, so for the 5 treatments there will be 1 D value each. The next step is to find out the D square, as in the case when you have calculated the variance and standard deviation. So here you are calculating the D square in each case. You are finding out the variation, you are finding out the square of the variation, D square. Then, there are 3 replications for each treatment. So, you have to multiply the D square with the value of the number of replications. You can call it small r, for example. So, the number of replications into D square will be giving you, as you got as D square in the case of finding out variance, in the case of a discrete frequency table, for example. So here you are finding out R D square, which is similar to F D square, as I mentioned, and you get the corresponding R D square in each row, which is the number of replications into D square, and you are finding out the total to get the sum of squares between treatments or sum of squares between samples. And in your example, when you calculate the total value of the R D square, for example, in the case of the total of the R D square, in the case of the 5 values, you get 243.48. 243.48 is thus the sum of squares between samples or the sum of squares between treatments in your present experiment. So that was the step of calculating the treatment sum of square, or the calculation of between treatment sum of square or between sample sum of square, and then comes calculation of within treatment sum of square. So there are 5 treatments, and for each treatment there are 3 replications. So for each value of the replication, for R1, R2 and R3, in the case of each treatment, you have to find out the corresponding D value. From the treatment mean, the treatment mean minus, or the column, the mean value of the corresponding replication minus the value of the corresponding replication minus the mean value of the treatment will be giving you the D here, and so you are calculating the D in the case of the first, the R1, R2 and R3 in the case of T1, T2, T3, T4 and T5, and then you are finding out the square, you are calculating D square. So you have several D square values, 3 D square values for each treatment, and totally there are 5 treatments. So there are 15 D square values, and they are totaled together. To get the sigma D square altogether. that is the sum of squares within treatments. So now you have calculated sum of squares between treatments and sum of squares between treatment and sum of squares within treatment. And the next step is construction of an Anova table. Construction of Anova table. And in the Anova table will be, as you know, there are several columns. These column shows the sources of variation, the sum of squares, and the corresponding degrees of freedom, and the mean square values. So the first row stands for the between sample variation or between treatment variation, and it is 243.48. And the within sample or within the treatment variation is 166.68. And in the case of the between treatment variation, degree of freedom is k minus 1, which is 5 minus 1, which is 4. And in the case of within sample variation, it is degree of freedom is n minus k. It is n is the total, and k is the number of treatments. Means 15 minus 5 is equal to 10. And when we divide the sum of squares with the degrees of freedom, corresponding degrees of freedom, you get the mean square, or you get the variance. So, sum of square between samples divided by corresponding degree of freedom. Here you get the mean square, which can be called the treatment mean square. And in the next row you get within sample sum of square within sample degree of freedom, and you get the mean square. So, the variance. So, you have now calculated the between treatment variance and within treatment variance. And the next step is the calculation of the F value. F is equal to variance between samples or treatments divided by variance within treatments. So you have calculated now both these values. Mean square between samples stand for variance between samples, and mean square within samples stand for the variance within samples. And the general assumption is that variance between treatments may be due to treatment differences, and the variance within treatments may be due to experimental error patterns. And because of that, the variance within samples or variance within treatments is also called error variance. So in that sense, you are dividing the between treatment variance with the error variance to get the F value. And here you have made the calculation, and it is 3.65. Then the next step is to see whether the calculated F value is significant, for example at the 5% level. For the purpose, we are using an F table, and the F table will be having two types of degrees of freedom. You see, there is variance between samples and variance within samples, or variance between treatments and variance between, variance within treatments being combined. So there will be a degree of freedom for the between treatment variance and degree of freedom for the within treatment variance. And as we have already seen, the between treatment degree of freedom is k minus 1, and the within treatment degree of freedom is minus k. So in the F table you get a numerator degree of freedom, which is the degree of between treatment degree of freedom, and also in denominator degree of freedom. And if you are here, you see the numerator degree of freedom is 4, and denominator degree of freedom is 10. So you have to find out the corresponding value of f. For df1 is equal to 4 and df2 is equal to 10. df1, the numerator degree of freedom, is equal to k minus 1, it is equal to 4, and the denominator degree of freedom df2 is equal to n minus k, which is 10. So in the table value you will get a corresponding the table you will get a corresponding value for f at 5% level, at 1% level, like that. For this experiment, let us take it at 5% level, and the value is the value is 3.48. So the table value, the critical value as per the table is 3.48, and your calculated value is 3.65. Means the calculated value is higher. Means that in the ratio mean square between samples, mean square between treatments is higher, significantly higher. Means the treatment has resulted in significant variation between the treatments. It shows that some of the variations, some of the treatments are causing high variation. Hence, we come to the conclusion that the treatments or those differences in the case of the fertilizer used have got significant effect on the growth of those plants. So now you have calculated the F value and you have found out the significance of the F value. And here you see there are several treatments, treatment 1, treatment 2, treatment 3, treatment 4, treatment 5, like that. And you see, are all these treatments mutually different, significant? We don't know. The only thing now we know is that there is significant difference when the treatments are taken together and analyzed for the ratio between treatment variance and within treatment variance. Maybe T1 and T2 are not significantly different, or T2 and T3 are not significantly different, and T1 and T5 are significantly different, like that. So you have to find out that also. And for that, there is another step, and it is the calculation of the lowest significant difference, LSD, which is also known as the critical difference or CD. So it is the smallest difference between two mean values, two treatment means or two sample means, that is needed to say that these two samples or that these two treatments show significant difference. So if the mean of the treatment mean of T1 plus the CD is equal to or higher than the second value, or then only you can tell about its significance. So you have to calculate the CD for the purpose, and you have to add the CD with the treatment means, and you have to find out whether whichever treatments are significant or which are giving significant difference, and whether T5, which is in which you use the highest dose of fertilizers, is more significant when compared to the others, and all that. So you can calculate the CD, and CD is calculated using an equation, and it is equal to CD is calculated from an equation in which you are multiplying the t value. You know, t is also a test statistic, a distribution of test statistic you will get in the form of a table. Here you are from the t table. You can find out the t at 5% level for the error degree of freedom. So t at 5% level, t 0.05 means t at the 5% level for error degree of freedom, which is the within treatment degree of freedom, multiplied with square root of 2 into within treatment mean square or error mean square divided by number of replications. It is equal to, CD is equal to t 0.05 for the second degree of freedom, df2, error degree of freedom, into square root of 2 into EMS, error mean square, divided by R, number of replications. And in the present experiment, degree of df2, error degree of freedom is 10, and from the table of t, you have to find out the value of t at 5 degree of, at 5% level of significance for 10 degrees of freedom, and it is 2.23. So you can substitute in the formula, you can substitute the values. CD is equal to 2.23, which is the t value you have obtained from the table, into square root of 2 into within treatment variance, means 2 into 16.67 divided by number of replications. And here you have 3 replications. So the CD has been calculated here. You are substituting the values in the formula. The t value, t 0.05 for error degree of freedom is 2.23, and you are multiplying it with 2 into 16.67 divided by 3. 16.67 stands for the within treatment variance, and 3 is the number of replications. So you get 7.43 as the critical value. The CD, the critical difference, is 7.43, and result shows that the means of each treatment, or the treatment means, show significant difference between them only if there is a difference of 7.43 between. So one particular treatment mean plus or minus 7.43 gives, or it shows whether it is significantly different from another treatment or not. So in this experiment, you can see that T1 shows significant variation from T4 and T5. T2 shows significant difference from T5 only. T3 shows no significant difference with any of the other treatments. T4 shows significant difference from T1 only, and T5 shows significant difference from T1 and T2. And since the mean value, the treatment mean of T5 is the highest, you have to see that whether adopting T5 as the most appropriate treatment, or T4 or anything like that, as the most appropriate treatment will be more useful based on your data analysis. So that was about the analysis of variance, and the test statistic is F, and you are calculating the F by using a formula. F is equal to variance between treatments divided by variance within treatments, and you are calculating the CD, also the critical difference of the lowest significant difference, and also you have now studied the use of this critical value and the use of the critical difference CD. Thank you very much.